Hi, welcome back. Already we have discussed about types of matrices. Some of the matrices I have discussed. Diagonal matrix, square matrix, rectangular matrix, scalar matrix. All those we have discussed. Now I'll continue the remaining types. After the scalar matrix, once I want to say initially in the beginning, I have to say this row matrix and column matrix. Row matrix means types of matrices. I am continuing. Types of matrices. Row matrix. Row matrix means the name itself indicates row dominates. Row dominates. A single row. A single row matrix is called a row matrix. Row already I have discussed. Row means horizontal view. Suppose if I take a matrix A like this, A, B, C, D, it is called a row matrix because in that a single row is there, 4 columns are there, 1, 2, 3, 4. Hence its order is row number 1, column number 4. So columns number 4, 1 by 4 matrix. Single row, whenever there exists a single row, it is called a row matrix. Similarly, column matrix means a single column and number of rows can be any number of rows. Single column must be there, then that is called column matrix. Column means singular number. A row means is a single row. So column number 1. So column number of columns is 1. The type of matrix is called column matrix. Rows can be of any number. Suppose same matrix I am writing like this. In this only one column is there. Number of rows is 4. Horizontal view is called row, vertical view is called column. Many times I am repeating this. This is very important before you deal with matrices. So here number of rows are 1, 2, 3, 4. 4 rows, single column, so 4 by 1 matrix. That is called a column matrix. So row matrix or column matrix. Next type is triangular matrices. Triangular matrices, in that two types are there: upper triangular matrix, lower triangular matrix. Upper triangular matrix, first I am discussing upper triangular matrices. So a square matrix is said to be upper triangular matrix. A square matrix is said to be upper triangular matrix if and only if all the elements above the diagonal or in the diagonal are non-zeros. All the elements below the diagonal are zeros. If all the elements below the principal diagonal are zeros. All the elements in the level lower than principal diagonal are zeros and remaining elements are non-zeros. That type of matrix is called upper triangular matrix. Suppose if I write a matrix like this: 1, 2, 3, 0, 4, 6, 0, 0, 5. if I write the matrix like this, if you observe that matrix, it is a 3 by 3 matrix. If you observe this matrix, all the elements in the principal diagonal means this one. This one is called principal diagonal. All the elements in principal diagonal are non-zeros, and the elements above the principal diagonal are also non-zeros, and all the elements below the principal diagonal are zeros. Means existence of the matrix is on the diagonal, principal diagonal, and above the principal diagonal, upper triangular. It is a upper triangle above the principal diagonal. Upper triangle above the principal diagonal. Existence of the matrix lies there. And below all elements are zeros. I can write this in the notation that this 0 element is 2, 1. Second row, first element. This 0 is 3, 1. Third row, first element. This 0 is 3, 2. Third row, second element. All the elements, row number is greater than column number. Those elements are becoming zeros. Row number is greater than column number. Second row, first element. Row 2, column 1. Third row, first element. Row 3, column 1. Third row, second element. Row 3, column 2. Row number is greater than column number. Such elements are becoming 0. So I can write this as all elements Aij such that Aij equal to 0 when row number is greater than column number. Already I told row number we denote with I, column number we denote with J. When row number is greater than column number, that element is becoming 0. All other elements are non-zeros. Aij is not equal to 0 when I less r is equal to j. I less r equal to j. So that is an upper triangular matrix. That is a upper triangular matrix. Exactly reverse will be the lower triangular matrix. Means existence of the triangle will be from the principal diagonal and lower than the principal diagonal, below the principal diagonal. Matrix existence will be there. Above the principal diagonal elements will be zeros. Exactly if we write the reverse way, we will get the lower triangular matrix. Here it will change as I less than j. All elements will be zeros, where I less than j. Remaining elements are generally non-zeros. It can be 0. Sometimes 1 or 2 elements can be zeros also. But in general, triangular matrix appearance will be like this. Okay, now next. So with this main types of matrices are there. Still the types are there, like orthogonal matrix, idempotent matrix, involutory matrix, like that matrices are there. Before that, operations on the matrices and algebra of the matrices must be known. So after completing those operations and algebra of matrices, we can discuss those remaining types. Before that, so I'll discuss the algebra of matrices, comparison of two matrices, equality of two matrices. One thing, equality of two matrices, comparison of two matrices, and algebra on matrices means addition of matrix, subtraction of matrices, multiplication of matrices. So before that, I'll first define equality of two matrices. Equality of two matrices. Two matrices are said to be equal. Generally, equal means we will compare we know in the real numbers what is equality. In matrices, when we mention equal, first of all, they should be of same order. If left side matrix A matrix equal to B matrix, if you say A and B must have same order, one thing. Corresponding elements both sides, left side first row first element, right side first row first element. Left side first row second element, right side first row second element. These are said to be corresponding elements, means same position elements. Left side whatever the position element in that position, right side is it must be equal to the element in the same position. Those are called corresponding position elements. They must be equal. Then only we can say two matrices are equal. Two matrices are said to be equal. Two matrices are said to be equal. Said to be equal if they are of same order. If they are of same order, and corresponding elements are equal, and corresponding elements on both sides. Corresponding elements on both sides are equal. On both sides are equal. Corresponding elements on both sides are equal. Suppose A matrix is equal to A, B, C, D. B matrix equal to 1, 2, 3, 4. This is 2 by 2 matrix. This is also 2 by 2 matrix. First of all, they should be of same order. Excuse me. If I write A equal to B, that implies and implied by, meaning of that is corresponding position elements must be equal. Here first row first element, here first row first element. A must be equal to 1. Here first row second element, here first row second element. B must be equal to 2. Here second row first element, here second row first element. C must be equal to 3. Here second row second element, here second row second elements. D must be equal to 4. Then only we can say both the matrices are equal. If the matrices are equal, corresponding elements are equal. If the corresponding elements are equal, then we say matrices are equal. At the same time, they should be are of same order. Otherwise, we cannot compare the corresponding elements. If the order is different, we cannot compare. We won't get some positions. If the order is same, then we can compare the corresponding position of the elements. So, that is about equality of the two matrices. Next, algebra matrices. Algebra of matrices. Algebra means algebraical operations on matrices. Algebraical operations means addition, subtraction, multiplication, division. Of course, division of matrices will not be there. Addition, subtraction, multiplication. Addition of two matrices. Addition of two matrices. Addition of two matrices. Again, here also same thing. They should be are of same order. We can add the two matrices if and only if they are of same order, and corresponding elements are added. We have to add the corresponding elements. Then only we can say matrices are added. Unless we can't say matrices are added. Corresponding elements adding means they should be are of same order. So, to add two matrices, they should be of same order. They should be of same order. They should be of same order, and corresponding elements must be added. Corresponding elements in both the matrices must be added. Then we say, then the sum of the two matrices will be obtained. Suppose A equal to alpha, beta, gamma, delta. B is equal to 1, 2, 3, 4. Matrices of same order 2 by 2, 2 by 2. Similarly, you can 3 by 3. You can take 3 by 3 as well as also 3 by 3 A, 3 by 3 B matrix. You can add them. Whenever you add first row, first element in first matrix must be added to first row, first element. Corresponding position elements must be added. This implies A plus B equal to adding the corresponding elements, you will get alpha plus 1, beta plus 2, gamma plus 3, delta plus 4. When you add the corresponding elements, we obtain the sum of the two matrices. Similarly, when you subtract the corresponding elements, you will obtain A minus B, difference of the two matrices. Difference is nothing but opposite operation of addition. So remaining things are same. Resultant matrix also it will be of same order since we are adding the corresponding elements. Similarly, we can add three matrices. If A, B, C are three matrices, we can add all the corresponding position elements. So as addition is commutative in real numbers, so matrices addition is commutative. Commutative means A plus B will be equal to B plus A. Subtraction may not be commutative, but addition is always commutative. Addition is associative. If you add three matrices, result will be same. If you add them in different orders, satisfying associative property, addition of A plus B result added to C matrix is equal to addition of A matrix to the result of B plus C. This is called associative law. This will be true for matrices also, but subtraction will not be true. Okay, while adding or subtracting, corresponding position must be dealt. Corresponding position elements must be dealt. We have to deal with corresponding elements only. We have to add them, we have to subtract them. Okay, next. Very important thing, multiplication of two matrices. Multiplication of two matrices. So multiplication of two matrices, first of all I will explain with 2 by 2 matrix. 2 by 2 matrices, because many students will have some doubt, confusion in multiplication of two matrices. Multiplication of two matrices. Multiplication of two matrices. Multiplication of two matrices. To multiply two matrices, very important condition. One condition is there to multiply two matrices. Main condition, important condition is to multiply two matrices A and B. To multiply two matrices A and B, suppose A and B you want to multiply. Very important condition is number of columns in A, number of columns in matrix A must be equal to number of rows in matrix B. Number of columns in matrix A must be equal to number of rows in matrix B. Then only we can multiply the two matrices. Otherwise, multiplication of the matrices is not possible. Number of columns in the first matrix must be equal to number of rows in the second matrix. Suppose A is 3 by 2 matrix, B is 1 by 4 matrix. Multiplication is not possible. Multiplication is not possible. Multiplication is not possible because number of columns in A is 2 columns, number of rows in B is only 1. Multiplication is not possible. If they are equal, we can multiply. How we multiply? Just I am telling. Suppose A is 2 by 2 matrix, A is 2 by 2 matrix, B is also 2 by 2 matrix. Then multiplication is possible, AB product is possible. How we get AB product is, before that A is having number of columns 2, B is having number of rows 2. So condition is satisfied. So we can multiply. If I take A is equal to 1, 4, 3, 5, B is equal to 2, 3, 3, 2. If the matrix is like this. How to multiply? How to obtain AB product? In the first matrix, you have to take rows, these two. You have to take rows. Row 1, row 2. In the second matrix, you have to take columns. Column 1, column 2. In the first matrix, you have to take rows. In the second matrix, you have to take columns. So, while multiplying, first row in the first matrix into first column in the second matrix. Row 1 in the first matrix, column 1 in the second matrix. Row 1 in the first matrix, column 2 in the second matrix. Corresponding elements you have to multiply and add. You have to add. Next, row 1 multiplication is over. Next, row 2 you take. Row 2 into column 1. Row 2 elements into column 1 elements. Next, row 2 elements into column 2 elements. Row 2 elements into column 2 elements. This is the process you have to take. First, multiplication with row 1 into all columns of second matrix. Row 1 into column 1 of second matrix. Row 1 of the first matrix into column 2 of the second matrix. If column 3 is there, row 1 into column 3. Like that. After completion with row 1 in the first matrix, next you take row 2 in the first matrix, column 1 in the second, column 2 in the second. If 3 is there, column 3 in the second. Row 2, column 1, row 2, column 2, row 2, column 3. Like that you have to keep on going with the multiplication. How to multiply these elements? Now, row 1 elements, 1, 4. Column 1 elements, 2, 3. You multiply the elements individually and make them sum. 1 into 2, 2. 4 into 3, that is 12. 1 into 2, 4 into 3. Elements individually you multiply and add them. Next, row 1, column 2. Row 1 elements, column 2 elements. Row 1 elements are 1, 4. Column 2 elements are 3, 2. 1 into 3. First element here into first element. There, 3. 1 into 3. Second element here and second element here. 4 into 2. That is 8. Product of the elements, sum. Sum of the products of the elements in those rows and columns. Next, row 2, column 1. Here row 2 elements 3, 5. Column 1 elements are 2 and 3. Multiply the elements individually. 3 2s are 6. 5 3s are 15. Next, row 2, column 2. Row 2, column 2 is, row 2 elements are 3, 5. Column 2 elements are 3, 2. So it multiply the elements individually. 3 3s are 9. 5 2s are 10. This gives the product of AB. So product of AB is 14, 11, 21 and 19. This is the AB product. Okay. When you multiply A and B, the condition is number of columns. Here number of columns in A 2, number of rows in matrix B is 2. These two must be equal. These two must be equal. Resultant will be the remaining two order. Remaining order is 2, here 2. So product order will be the remaining order. In middle the condition will be there. This is the condition that must be satisfied. Resultant order will be, product order will be, AB order will be the remaining rows and columns. That is 2 by 2 matrix. Okay. This is the way of product of 2 by 2 matrices. You practice the product of 2 by 2 some matrices, some problems additionally from your textbook. Then we will discuss about how to multiply 3 by 3 and more number of columns and rows. Okay. Thank you.